First, I'd like to thank you all for coming back. I consider that a huge threshold to have crossed for my second talk. Well, okay, last time we sort of did a whole bunch of different types of math problems that had to do with astronomy. And I showed a couple of applets that sort of help make the computational side and the creativity side of working with these ideas a little bit more fun than just grinding out on a calculator every single possible model. Let's see, we talked about gravity last time. This time we're going to talk about, well, we're going to start out talking about dark matter. How's that for sort of jumping into the middle of the frontier of astrophysics? First of all, any questions sort of from last time about any of the topics or approaches or techniques or math? Applicability, relevancy? Okay. Well, last time, we talked about gravity. We talked about how astronomers figure out the masses for things in the universe using basically a fairly simple equation that Algebra 2 students should be able to profitably manipulate. The application problems are sort of far and wide. We also did a statistical study of the speeds of galaxies within a cluster of galaxies. All right, we did the mean median mode and all of that. I then made the comment that the velocity of dispersion, that 1 sigma speed that you get off of that speed diagram, basically relates to the mass of that cluster of galaxies, just as the orbit period of a satellite together with the orbit radius gives you the mass of the central object. It's because gravity is a scale-free force, it operates the same way on scales from people jumping on the surface of the Earth all the way to clusters of galaxies, 1 trillion times or more larger in scale. And when you have a power law force that's just 1 over r squared with no characteristic radius of interest, then you get this kind of behavior. I made the comment that you run into a little bit of a problem when you compare, for instance, if you look at the mass of a cluster of galaxies, and this cluster has a particular size to it. Okay, you figure out what the mass is as v squared over g. I always think rv squared over g. That's just basically the radius of the cluster. V is this, when you plot the speeds and you get this dispersion, this V is 1/2, so 1/2 the V width of the distribution, which is basically 1 sigma. So that's the same velocity. That's the same thing here. And it's the same sort of relative speed of these things compared to the speed of the center of mass of the whole cluster. So you can get the mass of the entire cluster. That's, stars, black holes, gas, anything that's in that region of space with this size that's producing gravity is going to contribute to this M. That includes things that we don't even know about yet. So this is an all-encompassing way of figuring out everything in that area or volume of space that's producing gravity at all. Now, the common sense idea in astronomy is that this total mass of everything in here is largely represented by taking the mass m equals m1 plus m2 plus m3 of the individual galaxies that are there. And from observing what these galaxies look like and doing some computations, you can pretty nearly figure out what their masses are. The problem is that the total mass that you get this way from all the obvious things does not match up with the total mass of the entire cluster. And this difference is on the order of, you're only seeing about 10% in the things you can observe contributing to the total mass of the entire thing. So there's a huge amount of stuff left over that you're not picking up by just studying the individual galaxies or even the gas that we can detect between the galaxies. And this is what we call dark matter. Dark matter doesn't just appear within clusters of galaxies, but it seems to be a kind of a very common property of actually individual galaxies themselves. If you try to figure out the mass of the Milky Way galaxy, for instance, using any of a variety of methods, and then compare that with the mass of the number of stars that you see in the gas, you also get a very big difference between the two. So even within the scale of a single galaxy, you have this really huge discrepancy between figuring out its mass gravitationally this way and actually doing it by counting up the number of things that are contributing to the mass and adding those things up.
Well, when you count the number of things, that's going to be based upon radio and light emission, right?
Yeah.
So what you're basically saying is that this is, if I understand you correctly, that this is matter that does not emit any energy, so it can't be accounted for through the means.
That's right. You know, it's pretty easy to detect stars, and we can do that rather efficiently in our neighborhood of the Milky Way. Yeah, because you see them for the most part. You can detect interstellar dark clouds because it turns out that in the infrared part of the spectrum, they're not dark any longer. They actually glow, and they're very easy to spot in the infrared. Other types of components to the Milky Way include very, very hot gases in interstellar space, and those can be picked up either with X-ray techniques or with radio techniques. So using the electromagnetic spectrum, we can pretty much identify all of the major components to the Milky Way that should be contributing mass and gravity, and we can add all those things up. And we don't get the right answer. We don't get this answer, and this is physically and intuitively the simplest way to weigh a galaxy. In this case, the V is the speed of the sun and the solar system around the center of the Milky Way. We know that number. It's 225 kilometers per second. The distance R from the solar system to the center of the Milky Way is already also known to within about 10%. It's about 8.7 kiloparsecs. So these numbers are known individually to better than 10% accuracy, but yet the discrepancy is basically a factor of 5. A factor of 5, not 5% or 50%, but a factor of 5. We see 5 times more material gravitating to producing the mass of the Milky Way than we see in the individual stars, gas, interstellar clouds, and presumed density of black holes and neutron stars, which are hard to detect individually.
Well, let's say something's at 1 degree Kelvin, and that way it's giving off practically no radiation that we can detect.
Yes.
Wouldn't it still reflect energy from other sources?
No, because it would,
Or at least absorb
technically
it so
what we
that you
say
can
is
see
that material would have to be optically thin. It would have to be almost transparent in order for it not to appear in basically studies of the sky that have been done to detect very cold gases at a few degrees above absolute zero. We do that when we map the cosmic background for the background radiation, which is about 3 degrees above absolute zero. And so we know what the Milky Way looks like at that temperature, and we can figure out the masses and stuff. So we don't get the right answer, and this really should be the definitive way of figuring out the masses for things in bulk in the Milky Way, or anywhere else for that matter, and it doesn't seem to work. For a long time, people thought, well, maybe there's something wrong with Newtonian physics, because this is based on Newtonian physics. So people tried to modify Newtonian physics so that it worked to predict the right numbers for individual galaxies. The only problem is that for every galaxy, you have to fine-tune Newtonian physics with an arbitrary constant that's dependent on each galaxy. There's no universal constant you can put in that gets the right answer for all galaxies. You have to have a separate constant for each galaxy to fit things properly. And then when you look at the universe as a whole, you run into the problem that that thing that you have added to gravity, to Newtonian gravity, which is this gmm over r squared formula, the thing that you have to add to that is a function of velocity in order to get basically this to work out and give you the right answers. And this thing has to be different for every galaxy. It also has to be different in different parts of the universe. The problem is that the theory that we use for describing the universe is called general relativity. That's the fundamental theory that describes gravity on the largest scales. The problem is that when you add, the problem is that general relativity, when you look at very, very weak gravitational fields and essentially flat space, you get Newton's law of gravity perfectly. If you add in this term at that limit and work backwards, you discover that all of a sudden the idea that gravity is a universal force and that all observers will measure it in the same way, that falls apart. The problem is that a velocity-dependent thing added to this no longer makes it what we call relativistically invariant. That is, no two observers will be able to agree on exactly what the right form is for the law of gravity in the limit of weak fields and stuff like that. So it's not a relativistic theory. And only relativistic theories have been shown to be really valid in describing a huge ensemble of observations that we have about the universe. So we're very reluctant to take a 100-year step backwards in time, get rid of relativity as an assumption, and then go back to a universe where every observer is unique and different from every other, and there's no universal laws you can talk about. That simply is not going to happen. But, okay, what we can do, I mean, this is a kind of an advanced discussion, but here's something that we can do to sort of bring things home. As an astronomer, the one thing that you can do is you can measure the speeds of materials versus distance. Really good at doing that. If you look at the Milky Way galaxy, you know, it's sort of this spiral thing, okay? And we are located somewhere out here. Here's the sun, okay? And we can measure, we can look out in different directions around us, and we can measure the speeds of material that's circulating around the center of the Milky Way. When we do that, we get a graph that looks like this. I'm going to put in the units. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9. 10,000 parsecs. Parsec is about 3¼ light years, so this is like 32,000 light years from the center of the Milky Way, and we live here at about 8.7. What we discover is that very close to the center of the Milky Way, the speeds for things are sort of increasing like so to about 200 kilometers per second. Here's 100. Here's 50. Increases out to about a kiloparsec, about 3,000 light years. And then it wiggles a bit. Each of these wiggles represents one of these spiral arms. So this is, we're located here. Here's the next spiral arm that's interior to the sun's orbit. Here's another spiral arm. And finally, we get into the galactic center, right at 0. This looks pretty good, you know. Things speed up until we get to a kiloparsec, and then they plateau out at about 225 kilometers per second. Nothing wrong with that. And then this is pure observation. The error bars on these things shown vertically are like this. All right, so this is all valid data. It gets a little bit hinky out here, mainly because there's so few materials in the far reaches of the galaxy that you can really glom onto and get both an independent distance and a speed. There are a lot of things out there you can get speeds for, but finding the distances to these things precisely is very hard because they're just clouds of gas and they don't have stars in them or anything. So this is the data. Looks fine. If we take our little relationship here, m equals r v squared over g, and take a look at that, well, let's solve it for what v is. V squared is gm over r. Okay, looks fine. Let's take it one more step. V equals square root of gm over r. Okay, what this says is that speed, rotation speed, should be proportional to 1 over the square root of r. So the farther away you get from the center of this thing, which contains most of the mass, the speed is going to get smaller and smaller by the square root of r. This mass, basically in this approximation, represents where the bulk of the material of the Milky Way is. The center of the Milky Way contains really the dominant share of the mass of the Milky Way. So this is the distance away from the center of the Milky Way, and this is the speed that you should have once you get to the point where most of the mass is inside your radius. And that happens at about this distance. Okay. And so this predicts that the speed should increase until you get to this radius, and then it should start to decrease again as 1 over r squared. Rather v. Now it doesn't do that. You can loosen this assumption that most of the mass is inside here and put some of it out here. I mean, after all, the Milky Way, if you looked at it sideways, looks like a bulge with a disk. And this is where most of the m is, but there's still some m in the disk. If you created a better model where you're incorporating this, and as you step farther out, more of the disk mass is contributing, you can improve this somewhat, but you get a curve that looks like this. Thank you very much. Not much of a big help. And this is where the actual data is. This shows that at any given distance away from the center of the Milky Way, stars and gas clouds are traveling much faster than they should if they were being bound by the Milky Way. So all of this stuff ought to be flying off into the universe, not being bound into this beautiful pinwheel shape that we see as the Milky Way. That's been around for billions of years. Okay, so that is a little bit of the math of it, but here's what we could do. What we could try to do is create for ourselves a new Milky Way. We're going to create a brand new Milky Way. What we have to do is we have to find a solution to this equation. V equals, and it's going to be 225 kilometers per second. Okay. And that has to equal the square root of gm over r. Now, r is a variable that we adjust, but m is something that we could also adjust too. And the idea is that we're going to find a solution for m of r such that the resulting v is always constant. And by basically doing the math here, we get 225 squared equals g m as a function of r over r. Okay, and moving things around, we get r times 225 squared over g equals m of r. What this says, this 225 squared is a constant, this is a constant, so it says that if we have a galaxy where the mass in the galaxy increases linearly with the distance from the center, so it looks like this. If we plot that, here's mass. If we create a mass model for the Milky Way where mass increases linearly with distance, that behavior in mass will counteract the natural tendency of the 1 over square root of r, and you'll get a constant velocity. Okay? And all we've done is basically algebra 2 at this point. Just basically solving an equation, finding what m of r is. This is an extremely powerful technique, and the thing that happens here is that if you use this kind of a mass model, you're only able to account, for instance, for the mass down here. This is the observed mass, and this portion is the dark matter. All right? So as you see, the farther out in the Milky Way you get, the more dark matter there is between you and the center of the Milky Way. You can actually take this one better, okay? And you can ask, well, all right, this is what the mass of the dark matter looks like. What does the density of the dark matter have to be like at any given place? Well, we've got we have 225 squared times r over g equals m of r. But we can write m of r equals density times, and let's make it a spherical cloud, 4/3 pi r cubed. Okay. If we then put one into the other, 225 squared r g equals rho 4/3 pi r cubed. It's squared. Bring that down here. We get an r squared down in the bottom to live with the g. We also get a pi. We also get a 4, and we get a 3 up here. That's the density as a function of r. So what we can now do is say, this is the r. We select an r here, okay? And we use this formula, and it will tell us what the density of stuff in the Milky Way is at any given r. Now, density is something we can measure locally. You know, you take a region around the solar system out to a few light years, you count up all the stars, count up all the gas, and you get a density. And this is where this whole concept of a dark matter halo for the Milky Way becomes something local that we can measure right here in the solar system. Because we measure it by trying to figure out everything that we know that contributes to this, and what's left over is the dark matter. And it should be everywhere. Because this halo is a smooth function, presumably. Okay? There are no other wiggles. I mean, this wiggle can be taken care of by just allowing for the known stuff in the spiral arms. So this wiggle can be basically made flat. And because it's flat, that means that the halo dark matter doesn't have any clumps and clouds and huge structures that would affect things. So there's an awful lot you can learn. And here, once again, I mean, this is algebra 2 and a little bit of geometry. But it just goes to show you, and I said this before, that if you're teaching a science or math class, it's really, especially in a math class, it's really easy to work with equations and things like that. But when you try to make real problems out of these equations, you have to learn a lot of overhead terminology because those variables mean something physically, okay? Because they're being used in a model of some physical thing that you're trying to represent in the universe. And in this case, the actual math is fairly straightforward. We haven't used calculus, we haven't used differential equations or anything like that, which everybody assumes that when an astronomer is going to talk to you, okay, bring out the calculus. But this is algebra. Algebra coupled with a little bit of physical intuition. And the intuition started when we tried to use this law for measuring the mass of the sun to measure the mass of the Milky Way, and we found it don't work. And so how do we have to change the mass in order to make something that does work? And we discovered the mass has to be a linear mass over distance. But then if we're going to model this as a halo, then we can use spherical symmetry and all that kind of stuff. This is a very important relationship in galactic studies. It's been fine-tuned quite a bit because we can do observations that, for instance, we can do things like this. Here's the Milky Way galaxy. Here's a neighboring galaxy. We calculate the gravitational force between these two, and we can basically use the speed of this galaxy to weigh everything that's between this galaxy and the Milky Way. And that will consist of basically the entire halo of dark matter within this particular radius. Currently, the measurements that have now been made and the models that have been constructed indicate that the total mass of the Milky Way is 1.2 trillion suns. Of this, about 225 billion is in stars and gas. And the balance, which is 1 trillion, is in dark matter. So dark matter constitutes like 5 times more stuff than what we find just in the stars themselves. Okay, and those stars are in the Milky Way. So there's this huge halo surrounding galaxies. I have an app. Yes?
If there were evidence that dark matter is lumpy, you just said, if I understand you correctly, that it's not lumpy.
Right.
If there were evidence that it was lumpy, what would that evidence look like?
It would look like this, if this thing would ever turn on. What we have here, we can look at clusters of galaxies. We can count the individual galaxies. The individual galaxies basically are moving within the gravitational field of themselves and the dark matter. Now, the neat thing about gravity is that it bends light. So if you look at galaxies and things behind the cluster, you will discover that their images are lensed and distorted. And with general relativity, you can perfectly account for this and figure out what the mass has to be that's causing the lensing. This was done for this particular object. This is called the bullet cluster. What we have here are 2 clusters of galaxies, which are shown in blue. These clusters contain dark matter. The dark matter basically is defined by the blue shade here and here, okay? And that's determined by the way that images are distorted from background things. So this is the predicted distribution of the dark matter as these blue blobs. What you see in between them is the X-ray light from heated gas. And understanding a little bit about the dynamics of this cluster, what we've concluded is that basically you had 2 clusters of galaxies that collided with each other, passed through each other, and are now on opposite sides. That's what we see here. Clusters contain gas in the galaxies and in their intracluster spaces. That gas collides between the 2 clusters, heats up, and produces these clouds. What is really interesting, though, is that we don't have all kinds of distorted blue stuff going on in this area. The only place that we still find dark matter after this collision is still where it used to be, where the dominant galaxies are located. And it looks like the dark matter was totally unaffected by the collision. So the dark matter particles basically passed through each other and didn't interact with each other at all. But all those little hydrogen atoms slammed into each other and fluoresced in X-ray light and were left behind in the collision, clearly affected by the collision. So this means that dark matter, you can't see it electromagnetically. It's not affected by the electromagnetic force. It's not affected by the weak interaction either, or the strong force, because that's a nuclear force. Apparently, the only way the dark matter interacts with anything is by gravity, by just the presence of its mass. Now you think of electrons, they have mass and electric charge, so they interact gravitationally and electromagnetically. And most things that we know in the world operate both gravitationally and electromagnetically. Everything in this room dominantly is the way it is because of the electromagnetic force. Dark matter apparently doesn't have any additional bells and whistles on it because it's only by gravity that it interacts. That's why you won't find teeny tiny structures of dark matter. You only find these big blobby things because it's hard for big blobby things to cool down. It's easy for matter to cool down and collapse because it cools down by emitting light, which is energy. Dark matter can't do that, so it's always hot, and it never really produces apparently very small structures, except things that are about the size of the halos of galaxies. Those seem to be the smallest things that dark matter can really produce. We can experiment with an application. Let's see. This is an application where you basically can adjust the central density gradient, that is the way that the density changes with R in the center. You can change that also for the halo component, and you add the two together. You use the fact that the sun is situated at 8.7 kiloparsecs, has a speed of about, in this case, 215. And what you can now do with these sliders is to adjust what the dark matter looks like until you get something that resembles the Milky Way. Okay, that's apparently not going in the right direction. This is going in the right direction. So we'll crank this down. Okay, now that doesn't look quite so good. So let's change the exponent of the central component a little bit. Okay, I can bring that over. That's a little bit too high. Bring that down. Maybe bring it up. There. So what we get is basically we get a 1 over r squared law for the dark matter halo, and that's what we got by algebra and calculation. So the students can verify that a very simple model that they calculate seems to work well when you sort of iterate a whole bunch of different possible models. The central exponent is essentially 0, which means you just have a dominant central mass as a blob with a sort of a finite size to it. And then as you get farther away, that mass doesn't change. So you can model this velocity curve. This white data is basically the actual data. And you can pull things down and modify them. This is a kind of a one-shot thing. Once the students have done this once, then you've basically exhausted this. But there are other kinds of data for galaxies that are even wonkier than this. And all you have to do basically is put those numbers into this column here, and they will change what this white looks like. And here you have the density distribution in terms of solar masses per cubic parsec. So at a distance of about where we are, we can look at, let me see. Okay, where did I put that? Oh, I put it over here. How clever. Okay, we have the density model. It says that out by where the sun is, the density is about 1 solar mass per cubic parsec. Now, what we actually observe is closer to about 0.2 or so when we count up the stars. So there we get the factor of 5. This gives you basically the mass of the Milky Way, if I've done this right. Now you get 2.2 trillion solar masses. That's a bit high. Actually, I'm not quite sure why it's that high, but anyway, it's a self-consistent calculation, so you can change these numbers, get different total masses. If you like, you can constrain it by what our actual mass is and then try to work backwards. But anyway, that's sort of what you get there, and it's kind of a fun calculation to do. Questions about dark matter? It's sort of come up a lot about, well, then what is dark matter? And we can talk about a little bit of science content here and not math, if you'd like, and I can kind of go over what the possibilities are if you'd like to. If you'd like to hear about ideas that we have.
That'd be great.
Okay, yeah?
I just have a question. I'm trying to piece together what the graphs are showing. If I'm seeing that graph right, it's basically saying the further out you go, you have a greater density.
Mm-hmm.
If it's affected by gravity, why is the greatest density not at the core?
It's dark matter. The simple solutions show basically that, where was this? I erased it. The density varied as 1 over r squared.
Yeah, the density
So
is
as you get
from
farther-
the middle, it's the mass that's getting bigger as you go farther.
Yeah, the total mass, because the volume of the spherical shell gets larger and larger the farther out. So the mass contribution by each shell gets bigger as you go out in the Milky Way,
Right.
even though the density doesn't
Because it's a
change.
sphere.
Yeah.
Yeah.
There are some interesting discussions that we can have about dark matter. It was originally discovered as missing mass back in the 1930s, but at that time they said, when we get smarter and have better technology, we'll be eventually able to actually count up what this stuff is. Well, we never got to that point. We wound up in the 1970s with finding dark matter even within the Milky Way, as I showed you with this rotation curve thing. And a lot of galaxies show that. Even galaxies where you can't really define a speed curve properly, they're irregular, they have really big dark matter halos. So at some level, dark matter actually influences the way galaxies look and whatever, complicated. To figure out what dark matter is, the rule of the game is, first we look at known particles. We look there first. The standard model looks like this. We have a collection of particles called fermions, and we have a collection called bosons. We can do photons are bosons, and they're responsible for the electromagnetic force. We have gluons, which are responsible for the strong nuclear force. We have the W plus, W minus, and Z0 particles, which are responsible for the weak force. And then we have the Higgs bosons, which are responsible for mass. We can talk about that later. On the fermions, we have the electron and its neutrino. We have the muon and its neutrino. And we have the tauon and the tauon neutrino. We also have 6 quarks, the up, down, strange, charmed, T, and B. So that makes 12 particles here for things that produce mass, things that we represent as, these are what protons and neutrons are composed of, and electrons are things that dress the cloud within atoms. And neutrinos are particles that you find whenever you have quarks decaying into lighter versions of themselves. If you have a top quark decaying into a strange or a strange into an up, that interaction produces a neutrino because that's part of the weak interaction. In this category, we have one kind of a photon, 8 kinds of gluons, 3 kinds of Ws, and the 0, which is 1. So we have 12 plus 1. The Higgs will count separately. So 12 plus 12 is 24, gives you a total of 25 known particles. And of course, these particles have antiparticles, so that doubles the calculation. There are antineutrinos and things. There are anti-Ws. There are anti-gluons. The photon does not have an antiparticle. It's its own antiparticle. So it's not quite double that. Well, we can look at these known particles and ask if any of them are candidates for dark matter. The answer is none of these, because these live inside of the known forms of matter, which we've already added into our tally. Muons and tauons, they decay, very short-lived, so they're not going to be around long enough to form a halo of a galaxy, which takes billions of years. That leaves electrons. Well, you can't have free electrons. They have to always be partnered with a particle of the opposite charge. Otherwise, you'll have a net charge somewhere in the universe, and everything else will rush to make it neutral, because the electromagnetic force is 10 to the 40 times stronger than gravity. So it can't be any of these things. The next thing you can look at is the neutrinos. The way that neutrinos could work is that the dark matter needs mass, and the neutrinos, if you give each neutrino a teensy-weensy, minute amount of mass, there are so many neutrinos in the universe that they could add up to something really significant. The problem is that we know what we need in order to make dark matter out of neutrinos. We know how heavy each neutrino has to be, and the answer is it has to be about 10 times more massive than the known upper limits to the masses of neutrinos. So the known neutrinos don't work. For a long time, for a decade or so, people were frantically looking at getting better mass estimates for the masses of neutrinos, because if they could be shown to be like 18 electron volts instead of less than 2, then 18 is a good number for dark matter. But that has been basically thrown out the door. So that means that here we got dark matter. It's clearly present in the universe, unequivocally, but there are no known forms of particles in the Standard Model that we can bring in to explain dark matter. That's a dramatic sort of a statement, because in the past, whenever we had issues with mass in the Milky Way within small areas, we always used to say, well, you just add in interstellar clouds or gas, which are made out of this stuff, and electrons, and basically that makes up the difference. And usually it did in many situations. But on very big scales, that seems not to work any longer. So dark matter is not a known particle. It's something new. Now, what does a new particle look like? Well, new particles are things that we see from theoretical considerations. We predict what new particles ought to look like, and then we go out and see if we can find them. This strategy of taking existing understandings in quantum mechanics and nuclear physics and extending it and then trying to find a match with the extension has worked really well. That's why we have all these quarks. That's why we have muon and tauon neutrinos, because these were predicted beforehand, and then people went out, made the measurements, and actually detected these things. Well, here we have the astronomers making the discovery of dark matter, but the connection between astronomical dark matter and what we've worked with before, you can't get there from here, at least not right now. Instead, what we have to do is try to find theories that look like the Standard Model, but at higher energy, they add in additional things. Additional forces, additional particles, additional possibilities for how things can decay. And so one of the most impressive ones is called supersymmetry. Okay. And in fact, there is something called the minimally supersymmetric Standard Model, MSSM. Basically, it's like the Standard Model, but it has the principle of supersymmetry added into it, which makes for some additional things that go on. For instance, each one of these particles that you see here and here has a partner particle. And if we were to look at masses, this is the mass of a proton. This is 1,000 times the mass of a proton and 10,000 times the mass of a proton. Most of our physics would be sorted in this area here. Okay, up to about the mass of the proton, we know what the particles are and the forces, and this is the standard model. At about 1,000 times the mass of a proton and higher, we have the only good candidate is called MSSM. And that predicts that there should be particles that have masses between 1,000 to 10,000 times the mass of a proton. Okay. The most massive particle that we know about right now is called the top quark. It's at about 180 times the mass of a proton. And the Higgs is at about 125 times the mass of a proton. So all of the things that we know about are, well, it's 100, is sort of in this range here. When we get out to 1,000 and 10,000, we can take this model and bridge it out into this new energy range, but we're not going to be adding any new particles because that's it. With supersymmetry, we can add new particles. The particle that has the lowest mass is called a neutralino. And it's about somewhere about 3,000 times the mass of a proton, or 3 TeV as we like to write it, very crudely. This is a neutral particle. It interacts only gravitationally, according to the theory, and it would be a perfect match for dark matter. The problem is that the Large Hadron Collider has already looked at this energy range and has not found anything. In fact, it's already gone up to about 5 to 6,000 times the mass of a proton. And aside for finding some interesting tweaks in things at high energy, it has not found any new particles other than the Higgs at 125. So right now, there seems to be nothing between about 125, well, the top also is there, 180. And up to about 5,000. So where is this best candidate for the dark matter particle? We don't know. It could be heavier, but that's another version that's not a minimal version of this. It requires more bells and whistles, more complexity and things in order to fill up with more particle states that you can then go and look for. So it's a real dilemma. We don't know what dark matter is. And our best theory that would predict that there's something going on has in it something called supersymmetry, which hasn't even been demonstrated to be a symmetry of nature yet. So, that's a kind of a twofer. Not only don't we find the particle, but we don't even find the fundamental symmetry that allows you even to predict that the particle is there. So, again, we're kind of caught between a rock and a hard place, theoretically and observationally.
Two questions. How would you detect a neutralino?
Very difficult.
Okay.
Basically, I kind of misspoke. It interacts gravitationally and with a weak interaction. It has no charge, so there's no electromagnetic interaction, which is a very strong one. So what they have to do is they have to sift through trillions of interactions and find those that don't look anything like our normal, interactions that we expect, and then look for that oddball one. And from the oddball one, they can figure out, well, what had to be the mass of the particle that was involved. And if that mass turns out to be, in this range, then that's a possible detection of this. But so far, they've been running these. They ran these experiments for about a year and a half, and there are about 4 or 5 different experiments now that are actively looking for the dark matter particle, if it's anything like, this kind of an idea. Haven't found it yet. So when the collider starts up again in 2015, that's going to be the main thing that it's going to be doing. Hopefully, for the $7 billion invested in this huge machine in Geneva, required about 100 countries and huge amounts of collaboration. It basically revolutionized computing on planet Earth, network computing. They're going to get hopefully 2 results out of this machine. In previous machines, you got dozens and dozens of results that were fundamental to physics. Here, the first one that they got was the Higgs. I mean, you could retire the machine on that alone. But if they can find one of these supersymmetry particles, that will just completely revolutionize physics. Because it'll say that, yes, in fact, this idea that was hatched back in the 1970s actually is something that the universe has decided to play with. Okay. Just as for the Higgs was discovered back in 1964, and it took close to 50 years from prediction to actual detection. That's the longest running interval between prediction and detection of any particle. So, it's the way things go. You just have to be patient, and you have to be willing as a society to invest in this adventure. But in this case, the Higgs particle is associated with the reason that things have mass and inertia. This particular particle is going to be an explanation for where the other 80% of the mass of the universe is, which is equally fundamental. Because it's kind of stupid in astronomy. We spent our entire life, sort of looking at things through a telescope and then realizing in the end that this is only literally 4% of the gravitating stuff in the universe. It's basically dust and floating in air. And what is really important is what the air is doing, what dark matter is doing. And you always, in the past, had an idea that, well, if I just figure out the motions for things, then that basically is going to tell me something about the future of the universe. But in this case, that's not the case. You really have to take what we see plus this dark matter together, plus this other thing called dark energy, which is also unobservable. And so we're entering into this kind of weird 21st century astronomy where it's taken us hundreds of years to realize that what we're seeing around us is only a small portion of a vastly much more complicated universe, most of which is invisible. It's, I don't know, kind of weird. Yeah.
I'm guessing people have already debunked this, but could you have finely distributed black holes which only are gravitational?
No, because black holes are ultimately made out of these things. That's how they formed in the universe. If you go down to individual things like solar mass things, those are produced by supernovae, and supernovae are what happens when you collect a lot of this stuff together to produce a star. So you can always track a black hole down to its origin, which usually is in something in this area here. You can't have dark matter black holes. Because given what we know about dark matter and the way that it operates, it can't make anything that small. It has a tough time making halos the size of entire galaxies, let alone, things the size of, stars and whatever. So we know a little bit about it, but the things that we know are at such scales that it's hard to relate them to things that we can work with in our labs. So that's a little bit about dark matter. Yeah, a little bit. That's a lot more than you probably bargained for. Let me just, yeah.
I recall some speculation, and I don't know if it goes beyond speculation, that maybe dark matter is actually not matter in our universe at all, but maybe the effect of matter in a parallel universe that simply they can't touch each other.
Yeah, there are a lot of ideas like that. The problem is that they're not testable. It's a real challenge. Theoretically, ideas come out of mathematical sort of speculation and extension, but you can never really be quite sure whether or not what is coming out of the mathematics has any real resemblance to the real world. I mean, that's the art of making mathematical models of things in the world. These ideas that require additional universes or multiverses or parallel dimensions or 10 dimensions and stuff like that, those are interpretations of mathematical ideas that have not really been tested within our universe. And so the question is, you know, if most of your ideas have to do with things that are outside of our universe, how then do you go about making any kind of sensible test of these ideas? You don't. You can't, because they're permanently outside of our horizon for testing things. So, you know, it becomes you can't hold the mathematical idea accountable to the same kind of observations that we do for other things. And so that's why these ideas that would help solve this problem, there's not one, there are generally many ideas that would solve this dark matter problem, but none of them have additional testable factors associated with them. The proponents argue, oh, well, yeah, sure, we have testable things. Our idea makes a prediction of what the standard model ought to look like in terms of the particles and the forces. That's kind of a prediction in retrospect. You know, it's not a real anticipation of something, which would be a much more powerful thing. If, for instance, these ideas could predict a whole other rank of particles, which we observationally then went ahead and discovered, then that would sort of lead credence to at least these ideas being in the right direction. But still pretty provocative, because they have all these other implications. That's what happened with the inflationary cosmology idea, that inflation helped solve a whole bunch of thorny issues in Big Bang cosmology. But if you work with the math, you're led to this idea that there are literally an infinite number of universes out there, which we now, some of us call the multiverse, and we're just basically one realization of the way things could have come out in the Big Bang. And other realizations that might be currently existing, there could only be maybe two fundamental forces in addition to gravity, or maybe only an electron, or maybe only, you know, it could be variations on a theme, you know, all over this meta universe. And the reason that we're seeing the world that we live in the way it is because there's only a small number of these realizations that lead to living things that can become sentient and aware of their environments, you know, to the point where they notice how strange it is that leaves are green instead of, you know, purple or whatever. There are always going to be new ideas, but testability is the main thing. And it's not just because you're a hard-nosed scientist. It's like, what else can you do with an idea other than test it? And if it doesn't work, move on.
Let me ask a follow-up. So far, the defining characteristic of dark matter is that it only interacts by gravity and appears to have no other observable properties. Correct me if I'm wrong, but it seems to me that any real matter in our universe would have to have some other properties besides gravitational interaction. I can't even begin to envision what it means to say there's matter that doesn't have some other interaction capability.
The kind of matter that we're all familiar with partakes of basically all of these interactions: the electromagnetic, the strong, the weak, and that's why the world is such a colorful, diverse, interesting, with different types of packages for how this matter is put together, and with all this different kinds of information that's coded in structure. That's because we have largely the electromagnetic interaction and things like that. If we did not have the electromagnetic interaction, the only way that we would see each other is by our gravitational forces on each other, which are extremely weak. We would, for instance, without the electromagnetic interaction, atoms would not be held together, molecules would not be held together. Nuclear particles and quarks would just be free things in the universe, because the gravitational forces between things are so weak that they don't allow things to build up very large structures. So with only gravity, you're left with a very featureless kind of a world, and a world where there aren't things that can relay information back and forth. So yeah, that's how you would think of it. I mean, you still have matter present, but it's in such a distributed amorphous form that it doesn't contain charge or any other kinds of factors other than mass. Mass, which is complements of the Higgs field, and so that would be the only thing left over. And without the Higgs field, you don't even have mass. You know, when you actually do the calculation, a 100 kilogram human being basically only represents about 4 kilograms of actual mass. The rest of that stuff is in the binding energy of the fields that make us up, which are inherently invisible. So only 4% of what's on your bathroom scale is really ponderable mass. The rest of it is in energy in fields, which is kind of an intangible thing. So we're sort of one step away from not having mass ourselves. And the question has always been, well, why is there still this 4%? And the reason there's this 4% is because we have, throughout all space, we have the Higgs field, which acts kind of like molasses to slow things down a little bit. And that slowing down is inertia, which we see as that 4% of mass. So it all hangs together in a kind of a nice picture, but it leads you into a kind of a strange perception of the world. You know, if you change the electromagnetic force even a little bit, we wouldn't be here. We'd be different types of packages of material. You know. Yeah.
Do we see any effects of dark matter on a local level, like in the solar system? Where there's massive split?
No, haven't seen anything yet. There has been some discussion about the strange behavior of the Voyager spacecraft as it's gotten farther from the sun. Apparently, it's traveling a bit faster than it should if it were just gravity from the sun slowing it down. So people say, aha, gravity is not a Newtonian force, there's something going on with it, and that's where these other folks got in there and said, oh, okay, if we have things that depend on velocity, then we can model that and halo of the galaxy and all that. It turned out that the reason that the Voyager spacecraft is traveling slightly faster than before, than you'd expect, is because in a very strange way, there are a couple of items on board the Viking spacecraft, the Voyager spacecraft, which basically are painted to absorb sunlight. And so what's happening is that sunlight, even in the distant reaches of the solar system, is being absorbed by these things and producing a very weak rocket effect. So it's basically light from the sun is actually pushing, you know, on the Voyager thing a little bit faster than one would expect if you didn't include that. And that basically allows for the whole thing. There was also discussions about outgassing and venting of volatiles and things like that, but those effects were not as important as just light pressure from the sun at that distance, you know. Yeah.
So do people think that dark matter is attracted to a galaxy, or does the galaxy form because dark matter is there?
Yeah, because,
kind of a chicken or the egg.
well, that's a very good point. What the models show is that dark matter first establishes where all the gravitational wells are, and then ordinary matter falls into those wells and stirs around and becomes galaxies and clouds and stuff like that. And so they've been able to model this with a supercomputer. And what they do is they start out with a Big Bang as sort of this uniform expansion of ordinary gas and dark matter. And then they watch it gravitationally evolve in time. And what they discover is that it tends to form into filamentary structures. And if you adjust the parameters within reasonable tolerances, you get a universe that looks like ours. If 25% of the gravitating mass is in dark matter, 4% is in this stuff, and 70% is in dark energy. So we basically use our entire visible universe that we see today as a boundary condition for figuring out exactly how much dark matter there is. And we come up with numbers that are comparable to what we get if we look at individual galaxies. So there's a consistency there. And whenever you see consistency, especially on dramatically different scales, you get very excited as a scientist because you begin to think that, well, there's some underlying physics that I'm accurately modeling that tweaked one way gives you galaxy halos, tweaked another way gives you, the general patina of things in the universe that we can detect. And that's where we are now. It's, basically finessing the age of the universe by doing these observations, and so it's 13.85 billion years. Who knew that one can estimate something like that to such a tolerance, 10% or less. Any other questions about dark matter and gravity? The next thing we can talk about is rocketry, which is a whole other sort of subject. Yeah.
I have a question. So maybe this is just like a gross oversimplification, but so the whole dark matter theory is kind of a result of mass that we suspect must be there for the model to work, but that we can't find.
Yeah.
Is that sort of a good summary?
Mm-hmm.
So,
Well, the observations say that the stuff is there.
so
Yeah. Mm-hmm.
why must it be mass and not a force that we're not aware of?
Why isn't this the result of a new force in nature that operates not at the scale of gravity, but somehow at an intermediate scale?
Possibly. Why go to a, yeah.
That's an extremely good question. Why do we look for particles instead of new forces? Well, the reason is that, and in fact that has been looked at, to whether or not the presence of these dark matter halos is actually just a statement that there's a new kind of a force that's sort of between gravity, which is super weak, and the weak interaction, which is the weakest of these. It's often called the hyperweak force. The problem is that the only way you can get that kind of a force in our current understanding is it cannot be a force that's represented by a power law,
By what?
by 1 over r to the n. This is a power law.
Right.
The only way that one can self-consistently put an additional force of nature into the picture that operates at that kind of an intermediate scale is if you make it some kind of an exponential where you have x over h, where h is a characteristic scale. This is the way the strong force works, and that h is 10 to the minus 14 centimeters. So once you get to distances beyond 10 to the minus 14 centimeters, the strong force becomes very weak and falls off very quickly. So that's why you don't see it in the rest of the world. This hyperweak force to make galaxy halos would have to have an h that's on the order of about 100 kiloparsecs. But then if you put the same force into this cosmological picture and try to run these cluster simulations, you get really completely ridiculous results. They don't look anything like clusters that we see around us. If you run it backwards and use the clusters as a constraint on what this force ought to look like, you get a different law that doesn't work for halos of galaxies. You can't seem to get both by putting in this hyperweak force that works at a long range, but not at a cosmological range like gravity.
Well, the thing that sort of triggered that in my mind was what
Yeah.
you said about our bodies are basically 4 kilograms of
Yeah.
mass. And that's sort of the same thing that you're talking about in these galaxies. We can only account for
Yeah,
a small percentage there.
right.
And then you said our bodies is because of the other forces all netted together.
And there's also a 4% genetic difference between us and chimpanzees. 4%,
Well, yeah.
some things are coincidental 4%, others have profound meanings, and it's like we don't know which is, in this case, yeah, well, there might be a connection between the two, but we can't see what that connection is at this point, because there's some ingredients that are missing, and the biggest ingredient is that we haven't been able to independently discover what dark matter is other than in its cosmological setting. So it's not a force in the standard picture here. It's more a force related to gravity, which is something that we're trying to incorporate into here, but we can't do that so far. So we don't even have the math. All we can do is do these kinds of back-of-the-envelope calculations and try to figure out the properties by playing with things that we already know and extending them a little bit. So anyway, yeah. This has been,
Metaphysical question?
I'm sorry, yeah?
Can I ask you more of a metaphysical question?
Oh,
Do you see
uh-oh.
this as, this crisis in physics that's similar to the crisis that started off in the 20th century? Or is it totally different? Like, do we need a whole new theory to solve these problems?
Yeah, we can't understand dark matter and dark energy within the standard model. And the standard model has been our crowning achievement after 100 years of experimental high-energy physics, to suss out, what the particle family looks like, what their forces look like, and also ultra-precise theories, mathematical theories for how these forces actually behave. I mean, collectively, this standard model, in parts, is good to about 12 to 15 decimal places in accuracy. It's really hard to say, okay, trash that, we have to start all over. It ain't going to happen. What's going to happen is that we're going to start with that, learn some gimmicks from how this system works, and then try to extend that just a little bit more. And that's what this supersymmetry does. All right? It just extends it a little bit more to slightly higher energies to make predictions. So far, its important predictions haven't been verified. And we don't even know whether or not that symmetry exists, because we don't see evidence for it in the places that we know how to look right now. So we are in a little bit of a crisis. It's starting to look a little bit like, we're sort of through with gingerly stepping up to a problem. We have to take really big, huge steps now in conceptualization. In calculations, we can't just sneak up on an answer by adding one more term that we evaluate, because that's what we've done with quantum electrodynamics, with the strong interaction, and with the weak. Those are called perturbative theories, because we basically use the theory to drive calculations that add additional terms, and we evaluate those to get additional precision. We don't have yet a theory that calculates what in mathematics you call the asymptotic value all at once. We have to keep sneaking up on the value. The only way that we know what the asymptotic value is by going out and measuring the mass of a proton and saying, okay, that's what it is, but we don't have a theory that you plug in a number that gives us that. It gives us a whole bunch of numbers in a series that we have to add up, for as long as we want to run the calculation to get better precision. We're at the point where I think certainly our understanding of gravity is hampered by the fact that we don't quite understand what quantum mechanics is. Feynman said that we use quantum mechanics, but nobody understands what it is. And this is a Nobel physicist who actually created single-handedly an entire area. and if the general idea is that we don't really understand what quantum mechanics is, we use it as a tool, we can make ultra-precise calculations, but fundamentally we don't understand what it's telling us about the physical world. But if we look at what some of the things are that it's saying, our physical world is nothing like what we imagine. There are principles of operation that make absolutely no sense to us. And one of those things is, as I said last time, gravity is a key part of this. Whether you start with an already existing geometry and then add something on top of it, or whether you say that you have to create it all at once from the bowels of the theory. Those are two approaches that lead you in two different directions, yet they can agree on certain types of answers, like the information content of a black hole or other types of things. So clearly, these two different approaches that use two different mental visualizations of fundamental things can lead to the same kind of a thing. So there's some kind of a dictionary of going from one set of ideas to another. There's a correspondence between these ideas, but they're written in two different languages. That's what we have here. We've got the language that gives us this wonderful theory and consistency, but then we get this red herring of dark matter. We don't know if that is going to entail a completely different way of looking at things or if it's just a little bit of an extension. And that's why the next 3 or 4 years at the Large Hadron Collider are going to be very important. Because if we do find one of these really heavy particles and it turns out to be the neutralino, then we've solved all kinds of problems all at once, plus we set physics on a completely new, verifiable trail of finding new ideas and new things in the world. If we don't find it, that's going to be a real problem. That will be almost as revolutionary as not finding it at all. Because people have been doing supersymmetry theory since the mid-70s, and a lot of string theory is all based on that. If this goes away, string theory goes away too. And there's been a lot of investiture by young postdocs and tenured faculty in sort of working out all the mathematical bells and whistles for string theory. So that's why, certain key observations, when verified and really established, can really transform the future of a field like this. Anyway, so I don't know if that's metaphysics, but it's sort of a big step back for those of you that teach physics. Yeah.
Good point to take 10 minutes.
Yeah, sure. Oh, yeah. Actually, what time is it?
9:35.
Oh, okay. So let's take a break, and then we can. It would be. I could sort of go 2 different ways on here. I mean, we can either talk about ballistics and rocketry, or what I think is actually more important is, how do we make sense out of all this, and is this sort of appropriate content for students to be exposed to? I've heard from some high school teachers that by the time you folks see students that came out of middle school, the middle school kids don't know how to do word problems and are sort of ill-prepared, for actually working with your content area, thinking symbolically and quantitatively. And I find it hard to believe that that's sort of the case in general, but I mean, is that sort of your experience? I mean,
I don't really think it has as much to do with their preparation
Right.
as it does to do with the level of thinking they're willing to put in.
okay, so if you ask them to do any kind of a problem, the first thing that they're going to do is try to use the simplest math they know how to do, which is add, subtract, multiply, divide.
Not even
No?
so much that, they just want us to hand them a formula to use with.
Okay,
They don't want to derive the formula.
all right. And they assume that every problem has a different formula.
Yeah.
They don't know how to generalize to classes of problems. All right, well, that's kind of a hindrance in
We have students that would rather rearrange a formula 5 times, write it all out, memorize those 5 ways and exactly what they're
Okay.
solving for, rather than take the one formula and just use algebraic methods to write it.
Right. Okay.
It's-
Is
I
that
don't know why.
is that sort of what you all experience? I mean, when students are confronted with an application problem, because all we've been discussing here are application problems, and albeit these are advanced application problems because they bring in, topics in science and astronomy that are probably beyond, what you're teaching, but perhaps not some of the nouns and verbs. It's just the context. But apparently, context makes a big difference for students. So, is it that I've been told that the way to engage students is to offer them problems that are sort of real-world, realistic problems that they can understand how they relate to things around them, that they're personally of relevance to them, or they can see themselves needing this information for their immediate future, that it also has, good social contact potential, so they prefer working in groups rather than as isolated individuals. I mean, are these all, is this just urban legend, or am I onto something? I mean, is this a way of sort of distilling student temperament?
Let me give you a perfect example,
Okay.
okay? We spent a long time talking about the midpoint of a segment,
Mm-hmm.
how to find it, why it's important.
Mm-hmm.
Nobody cared until Joey went out and got an airfoil for his car, and it didn't wind up in the middle of the vehicle. It was off to the side because they didn't find the midpoint successfully. And the mocking and the teasing that went on because, dude, it's just the midpoint.
Okay,
So they had
all right,
that kind of example
okay.
given to them. Now midpoint is relevant to everybody in our building
Yeah.
because we have the example of Joey who went out and messed it up.
The difficulty that I see, and this is my bias as a scientist, is that if students are only interested in topics that they can see an immediate connection with, then basically they've absolved themselves from learning about the vast breadth and scope of humanity's intellectual arts, music. I mean, because most types of music are not of interest to your students. So, but you still have to bring them in contact with this stuff because that's part of human culture. And students should be exposed to human culture on the broadest scale, right? And in science, you can come up with artificial problems that always involve their immediate world. Operating a bike or a car, or walking uphill, and potential energy and friction. But the world is bigger than that. And as a scientist, I always want to sort of expose people to the bigger things. It's
Probably, I hope that way, I'm sorry. I'll probably give you a longer answer than anybody here.
longer than ones I've given.
Wants to give. It's just the way sorry. What's driving us, what's driving 21st century testing, what's driving changes in curriculum that we face on a daily basis is that business and industry have gone to post-secondary education and then next have gone to secondary education and then are working their way backwards from their unfulfilled needs.
Mm-hmm.
They need people who can live in a quantitative world and who can recruit that capability to solve everyday work problems and interact
Right.
in a meaningful way on the job.
Mm-hmm.
The only exception to that I have found useful in my classroom is things with entertainment value.
Mm-hmm.
Because the generation of kids whom I face on a daily basis in my urban, below middle class, everyday environment,
Mm-hmm.
the only exception to that for me that gets kids in the right mindset are things that are entertaining. And a lot of my day, a lot of my year is consumed with, yes, satisfying these standards that have been imposed. We as a society are prioritizing our survival.
Mm-hmm.
And it has dawned upon the people who make widgets and design widgets in this country that they need people who are capable of making and designing widgets, that we're graduating people who are wholly, except for the top of the top, wholly incapable of doing that.
Mm-hmm.
And the way that I have to recruit people into that process is to make it as entertaining and as interesting as possible. And so this is a Venn diagram with some overlap.
Sure.
And there is hope for the viewpoint that you just
But-
articulated. And the hope for that viewpoint lies in
Right.
grabbing hold of people's imagination and bringing
Right.
them in and creating some excitement.
Right.
And there's no guaranteed way to do that.
Mm-hmm. Mm-hmm.
And a lot of us spend a large part of our time searching for ways to do that.
Mm-hmm.
I don't know if I answered
Yeah.
your question.
Yeah, I mean, I see where you're going with this, and to me, it just, yeah, I guess, I started out always being interested in the world around me. I mean, since I was like 4 years old, connecting snails in a box, and studying dinosaurs, and, I've always, and so I find it difficult to even fathom the mindset of someone who is completely uninterested in the physical world.
Intellectually passive.
You know, it's like, why is the tree green? I don't know, it just is, and what's for dinner? You know. And maybe I'm sort of the wrong person to be giving these kinds of courses, because I really cannot bond with students that are that turned off, because I just look at it with an enormous amount of pity and frustration as an educator that, you know, they are never going to see the passion behind anything other than their own immediate social needs and networks and human hubris and things like that. But then what about climate change? I mean, to me, I see climate change as being, I mean, maybe not exoplanets, maybe not standard models and gravity and rocketry, but at least climate change to me seems to have legs, you know, as a topic. And so that might be the vehicle, but, you know, there's only so much that NASA does regarding climate change. Me as a scientist, I do none of it, but I know quite a lot about it because intellectually I find it an interesting and socially important topic. So, I mean, are we all going to converge on maybe climate change as being the only other topic that students could be highly motivated to learn about? Or, I don't know, it's, yeah.
When we bring climate change into our students' awareness,
Mm-hmm.
we get comments like, well, if it floods, then the government will provide us with housing.
Uh-huh.
I completely
If
disagree.
it gets hot, the government will give us all air conditioning.
Uh-huh.
I disagree with that because I teach meteorology and I
Mhm.
spend basically an entire semester leading up to, you know,
Mhm.
our ending climate change, and I
Mhm.
make the kids debate on it, and
Mhm.
you know they have to choose a side, and it's pretty holistic approach to
Mhm.
why the climate is changing and what are we going to do about
Right.
it, sort of deal. And they get very involved with that topic. They don't necessarily get involved with a lot of other ones, but
Mhm.
if you make it, you know, so tangible for them, I mean, they get involved with stuff like that.
Well, I see climate change as being a kind of a Trojan horse, you know, or maybe a very big raft. You know, climate change is really very Earth and regional focused, but fundamentally what drives climate change is the sun. So you can raft understanding CO2 in the atmosphere, ozone depletion, ocean expansion, and sort of the different timescales for this onto a study of the sun and its changes through time. All right? And that leads to, well, why is the sun producing energy? And it does that by fusion. And then all of a sudden you've opened up nuclear physics into climate change. You know, but it, you know, intellectually it seems like the right way to do it, but ultimately that only takes you into a fairly narrow set of physical issues. You know, you don't do Newton's laws of, you know, force, 3 laws, you don't do Kepler's laws, you don't do a lot of these other things. It's always focused on climate change, which is not a dynamical thing in the same way as rocketry or colliding galaxies. It's a different kind of dynamics. It's energy flows, it's chemistry, you know, not a whole lot of momentum transfer. There's thermal heat transport, you know, which microscopically is momentum transfer. But yeah, so you can get lost in these minutiae, but again, you've gone way far away from where the students are going to be comfortable. And climate change by itself, you know, doesn't have enough connections into, you know, the physics or math standards, you know, to be the only thing that you need to sort of focus on. That's why you need kind of a diversity of fun topics. And for me, you know, as an astronomer, the next most fun topic after climate change is exoplanets, you know, life on other planets. Because that becomes another raft that connects up with climate change because you're looking for habitable zones now, you know, which is climate change. And so I can see, you know, now you've got 2 subjects which, like in the Venn diagram sense, have like opened up larger areas. And maybe you only need 5 topics that you need to worry about. And, yeah.
Even in the classes that I have that are the most attentive, the most motivated,
Yeah.
there is more, I think, than there ever was, and I've been doing this for 27 years now. And the trend is that the middle is falling out of the bell curve. That you've got a bump over here, a huge bump over here of individuals who really won't care whatever you do, or whatever
Yeah.
intellectual challenge, or whatever exciting topic,
Sure.
or whatever relevant topic you throw at them.
Yeah.
They're just there because they have to be there. And then at the other end of the spectrum, like I
Mhm.
said, the middle has fallen out. At the other end of the continuum, you have kids who make connections, who come from a perspective, a personal perspective that's willing to consider what you consider exciting,
Uh-huh.
you know, and will at least accept the challenge of grappling with it.
Right.
But the middle, in my classroom, I teach 10th and 11th grade primarily, in my classroom, the middle has fallen out.
Hmm.
And it's just, it scares the hell out of me.
What do you
Bottom
think?
line is it depends on where your kids are coming from.
Uh-huh.
In Pottstown, we know where our kids are coming from.
Mm-hmm. What, socioeconomically?
Depends on what level you're teaching your kids,
Uh-huh.
as far as how deep they want to get into it.
Right.
I know my approach to this, I teach special ed,
Mm-hmm.
and my approach is going to be try to give them, at least expose them to something
Mm-hmm.
with it on a very much lower level to where they understand it.
Mm-hmm.
And as a teacher, you're not going to get to every kid.
Yeah.
If you get to most of them, then you've done something.
Yeah.
You know, what you're talking about, what you picture in your mind, you obviously would be better at teaching postgraduate level
Yeah.
compared to high school special ed kids or
Mhm.
low-level kids, because
Mhm.
you're not, we got to deal with everything.
It takes a certain individual to be able to go there and see from the other pair of eyes,
Not even
you know.
just special ed, just
it's just-
basic ninth graders nowadays. They don't
Yeah.
even have to be special ed, because believe me,
Mhm.
they all think the same. They just don't think, they're just not intellectually as,
Hmm.
they all think the same.
Mm-hmm.
You know, outside of school, it's just how can you get to those kids
Mhm.
and deal with trying to teach them something that's
Mhm.
meaningful to what they need to
Mhm.
know? And bottom line is, do they need to know about astrophysicists?
Yeah.
No.
No,
But
I
is
mean,
it important
yes.
for them to know that there's galaxies out there,
Yeah.
and there's more than one,
Yeah.
and things are moving around us, and we're finding things daily?
Mm-hmm.
Can you go on and Google something and find something like that at their level? Yes.
Right.
So it depends on what we teach, and you teach biology, whatever it is, it
Mhm.
doesn't matter. It's what we can
Mhm.
try to get something out of this to take back to our classrooms.
Mhm.
And that's what I'm hoping to do.
Mm-hmm. Yeah.
Because I teach lower levels also, and because my students are so uninterested in so many things, we spend a lot of time in talking about, why do I care about this?
Uh-huh.
And one of the things that I explain to my classes repeatedly is that you're going to change jobs 5-6 times in the course of your life. So the fact that you don't need to know Algebra 2 techniques in order to go dig a ditch doesn't mean that 20 years from now you won't need to come back and relearn these Algebra
Right.
2 techniques later. So I get the freedom to expose them to all kinds of things
Mm-hmm.
because we don't know what they're going to be 20 years from now.
Sure.
We don't know
Yeah.
what they're going to need, and we don't know what they're going to rely on.
Mm-hmm.
Some of your brighter kids, some of your more self-motivated kids,
Mm-hmm.
they'll grab onto a concept or an idea, and they'll go forward with that.
Mm-hmm.
And the ones that don't care aren't going to care no matter what topic you
Right.
lay out in front of them. So you get to lay out whatever topics make you happy. And we lay out what we can
Right.
to give them a well-rounded view
Mhm.
of all the things that are fun.
I mean, does it help if the topics are connected in with current events that they've heard
Yes,
about? And
Absolutely.
Right.
that's an important hook for any of these things. Yeah, I figured out that much of it. And, you know, and when I look at newspapers, they do have, whenever they do have science articles, they're often about exoplanets or about, some new discovery. So I figure, okay, that's fair game. Students are exposed to these things. I might not find them passionately interesting, but at least they're part of current events. So, yeah, there's this sort of institutional pressure these days, especially amongst science research institutions, to make real data available to teachers and students. And I've always found that to be, kind of a double-edged sword, because data is not just numbers, and the way that you understand what the numbers mean is just not arithmetic all the time, and taking averages and finding, doing box and whisker diagrams. It's a lot more than that. There's an art form to working with data. So the question is, why are you exposing the students to a particular kind of real-world data, when you're not really prepared to give them the tools for making a deeper sense out of it? And so, but you don't want to keep giving kids artificial data, because you hear survey after survey that students don't respect contrived problems. They like real world things that they can see and relate to. So, if you're trying to work with real world stuff and real world data, you have to provide some kind of a tool that makes working with that as transparent as possible. So that's why I keep coming back to readily available tools like, Excel spreadsheets, because there you can put the data in and you can plot it any which way you want to find whatever you're looking for, and keeping things pretty general. But I'm not as convinced that most students at the high school level are really that familiar with Excel spreadsheets, nor see the point in learning how to do simple operations with an Excel spreadsheet, even though...
Advanced levels, I see a lot of kids who just, it's foreign to them. They know it. They've seen it in the toolbar at the bottom of their work screen, but they just have not been.
But with all the pressure from business to get kids connected in with things, I mean, business runs on spreadsheets, and you would think that they would be huge promulgators of, kids learning how to work with these things, because it's such a common tool. And it's an accessible tool if you want to do work with real data as well, because there's no other context in which you can work with real data other than an Excel spreadsheet, because there's just such a huge volume of it in order to flesh out a particular phenomenon. It's not just one point establishes the trajectory of a particle. You need multiple points, if not hundreds, to actually figure out what the curve looks like. So, I mean, is that something that institutions like NASA should be sort of supporting more, getting students more plugged in with working with spreadsheets, which sounds like, kind of an obvious thing. I mean, generally, education programs at NASA go light years beyond that concept and want to get you directly into the science concepts, the great overarching ideas like the ones that I've talked to, because that's where all the pizzazz of NASA and rocketry and things going up into space, can be really, demonstrated and done well. But it doesn't have any meaning unless you work at the basic level first and sort of establish what you're going to do with this information.
The skill set has got to serve
Yeah.
an end, and the end has to be articulated.
Yeah.
And I think that's true for you guys, but it's also,
Yeah.
at our level, we do a lot of us, I'm not going to paint everybody with the same brush, but a lot of the people who are not here today,
Yeah.
let's say it that way, and who are not in places like this, do a very poor job of articulating in their classroom what's important and why it's important. They're doing things the same way things were done in 1971. And some of them were born long after my career started, and they
Right.
should know better. And they're just not very good at articulating why, and they're especially at the secondary level, we tend to be subject specialists,
Yeah.
and it's like trying to get a 400 hitter to teach you how to swing the bat. He's never had to really think about swinging the
Right.
bat.
Yeah. Yeah.
I want a 270 hitter
Well,
to teach me how to swing the bat.
It raises a good point. I mean, you have all come down here from Pennsylvania as part of this program to get enrichment in science content, I guess. It's sort of been the general banner. You've been sort of selected in your school districts to come down here and spend, a chunk of your vacation time or summer, sitting in rooms like this, listening to content experts. But it's never really been explained to me, just between the two of us, exactly what it is that you're wanting to carry away from you. Are you wanting to carry away, some razzle and dazzle new ideas that you can bring to your students to get them excited? Are you more interested in an update on what's at the forefront? You're looking for hands-on?
It's all the above.
Well, we've done hands-on here with these. This is as close to hands-on as we get. We get these Excel spreadsheets, and we do occasional calculations. And that's sort of par for the course when you're doing, science and math combinations. If you're doing experimental courses, around here at NASA, experimental courses almost always involve, pop rockets or some kind of a thing, and we've been doing that for like 50 years, and okay, I've seen where that's gone as a scientist, and kids don't learn advanced STEM techniques by working with pop rockets. Pop rockets is fun, for about 10 seconds.
Very short.
But anyway, that's just my grievance.
So I'm a biology teacher,
Okay.
and the curriculum for biology is fairly set because we have
Mhm.
this test we have.
Mm-hmm.
But the subject matter for the test doesn't seem to include even the topics in biology that gain kids' interest. Like, I have to teach them about the Krebs cycle.
Yeah,
There's no reason why they would need to know the Krebs cycle in their everyday life.
right.
But I can't teach them anatomy because there's no time to teach anatomy.
Sure. Yes.
But anatomy is what engages them, and the Krebs cycle is boring as all get out.
Yeah.
So when I come here, one of the things I know that engages them is space.
Yeah.
When I say I went to NASA this summer, I get 20 eyes on me
Yeah.
because they want to know what happened. So I guess my point for coming here is because we have no astronomy, no earth science,
Mm-hmm.
because it's not tested.
Uh-huh. Yeah.
So I want to put these things that they're actually interested in into my curriculum to
Mhm.
help,
Well, which is why I've been collecting sort of surveys on teachers and what students like to hear about, and it always comes into these very stereotypical subjects of black holes, Big Bang, astrobiology, and so what I decided to do in this session with you folks is to show you examples of math, because that's why I was asked to do this, to show math examples that connect in with these things that the students claim to be so fascinated about, and to show that the relevant math is actually on grade level. If you're already taking Algebra 2, most of the stuff is just Algebra 2. So I think we're trying to get at the same thing. I'm trying to create a workshop course, that's sensitive to what students are interested in, but I keep getting the message that students say they're interested in it, but for about 10 seconds worth of an answer, and then they're off to some other interest that's more passionate, usually social media interest. So
They always say that you teach with the outcome in mind. If you look at the pre-test/post-test
Uh-huh.
for this endeavor,
Uh-huh.
then what our benefactors want is to ensure that we're not incompetent.
Mm-hmm.
What they want to ensure is that we know some of the basic equations that describe the motion of objects.
Yeah.
Is that we know some of the basic processes that move ecological cycles and
Sure.
some of the physiology and anatomy of cells.
Mm-hmm.
That's what they want to ensure.
Mm-hmm.
And I think, frankly, they're missing the mark. I think the vast majority of teachers are highly competent in those kinds of things.
Oh, yeah.
We really don't have that, especially I can only speak for the secondary levels and the colleagues who surround me on a daily basis.
Mm-hmm.
I work with some pretty damn competent people in that kind of material.
Right.
So they're missing the mark entirely. What should be happening here is that things should be presented that welcome kids into the processing and scaffold them up through the process
Yeah.
of using mathematical analytical tools
Right.
to answer some of those fundamental questions.
Well, yeah, this has all been a really good discussion. I'm thinking that probably should have had it before I started, although I probably would have been completely taken off my game if I had had this as the initial discussion with you. But that's, we can adapt for the next workshop. But yeah, thank you for your, your time. Yep, I'm sorry.
Question, Jordan, but I'll ask you.
Oh, sure.
When I was doing my lesson plans for the kids and all that, and I was here last summer over the course of the year.
No.
I felt like my kids, when I incorporated, I used the geodome, and I used like even we looked at algae blooms in May, and looked at real-time data to study photosynthesis and things like that. And my kids really liked it. But my trouble was actually finding it, because I feel like I went on that one website, or the Discovery Learning, and I kept getting the same 20 lesson plans.
Yes.
And it was just hard to find. I had better success going to Google and searching like nasa.gov and
Sure.
the thing that I wanted to
Yeah.
study. But it just took me the longest time just to find the lesson plans, to find the material.
Yeah.
And then we came here and we saw your math site.
Mm-hmm.
And it's just finding all the stuff. It just seems like it's all over the place.
Well, space math is basically no longer funded, so that's going to become an archival thing, and I'm not going to be adding anything new to it, which is too bad. After 9 million problem downloads last month, NASA's walking away from this. They, beats me, but I'm taking early retirement, I guess. But it's just it's very frustrating to work in the math area in an institution like NASA, just to actually be bloody frank with you. Because, most institutions brand themselves as being inspirational for kids, and the last thing that you want to do to inspire kids is to bring them in contact with math. That's the poison pill.
Well, you guys have a great graphics department, that's all.
Yeah, it's graphics, it's art, and that's good too. But, it is very frustrating, and you sort of do the best you can. I feel kind of strange in that as an astronomer, I gave up full-time research to do this, and I have no other partners in all of NASA as an $18 billion a year institution that also feel as passionately about math education, and I'm gone. I'm basically history at this point. And it's like, wow, great experiment, and, oh, whatever. So, I'm not going to be doing this next summer, and you probably are going to say, well, you probably shouldn't have done it this summer either. But, it's, you work with the resources that you have, and, I'm sort of glad that you all sort of stayed for the duration. And, when you go back, I just hope that you have a better sense that a lot of these great ideas in science have actually basically simple math associated with them, so kind of demystifying that. Anyway, thank you so much. Yep.